Hello, everyone, and welcome to the Vantage Seminar. As we start, I'd like to mention that this is approximately the 75th lecture in the Vantage Seminar, and the last 3.5 years were and continue to be a difficult time in the world, and I'd like to take this moment to thank all of the speakers for giving us the opportunity to focus on some beautiful mathematics. So today we're continuing the series on perspectives on Galois groups. I'm very happy to introduce Lior Bari-Sorker, who will be speaking on the discriminant of random polynomials. And Lior, is it all right if we video this talk?
Yes.
Yes, wonderful. And if you have questions about the math, feel free to ask them at any time during this talk. Okay, Lior, go ahead.
Okay, thank you very much. So today I want to present to you what is currently my favorite question in mathematics. It changes with time, but this stays my favorite question for a few years now. So let me just start immediately with the question. And you take a polynomial with plus minus one coefficient that you choose uniformly at random, and you compute the discriminant of this polynomial. And the question, can you show that the discriminant is a square with negligible probability? Let me do the discussion about this problem and some related problems in more details, okay? So, but this is in principle the question that I don't know how to approach. In fact, I'm going to talk about two problems here, and they can be put in a very general setting, but I took exactly the opposite direction, and I will just state them in two special cases, but these special cases are central, and if you solve these special cases, it's already very interesting. So the setting is the following. We choose a A0, A1. This will be the coefficients of a polynomial, and we choose them to be independent random variables, taking values uniformly in an interval of, let's say, between minus L and L, where L is some parameter. And we use these independent random variables to form a random polynomial, which is, I like monic polynomials. It's not necessary, but why not? So I take a random polynomial, a random monic polynomial of degree n, that the coefficients are chosen according to this independent random variables. So this is my random polynomial. And in this talk, I focus about the following probability that depends on two parameters, on the degree and on the size of the box that I chose. So I call it P and L. It's the probability that the discriminant of this polynomial is a perfect square, which is non-zero as an integer, okay? As Rachel said, if you have any questions, don't hesitate to stop me and ask, okay? And the first question is about this quantity, this probability when the size of the box, when L goes to infinity. And in this setting, we know that this probability goes to zero, but the question is how fast it goes to zero. And the second question is what I wrote in the first slide. If L is fixed, for example, L equal 1, do we know that the probability goes to zero as the degree goes to infinity? So in this setting, for example, if you think about L equal 1, so the coefficient can be 1, minus 1, or 0. And the degree goes up and up. And I wonder, can we prove that the probability that the discriminant is a non-zero square goes to zero? Okay, these are the two questions I want to discuss. But let me start with motivation. Why I'm interested these two questions. And one motivation is a picture by Sam Derbyshire that is so beautiful, and I think I show it in every occasion that I have. So what you see here are a calculation or computation of all the roots of polynomial with plus and minus one coefficients up to degree 24. And you see here something interesting. First of all, we see that the circle that you see is the unit circle. The holes that you see are roots of unity, and you see all kind of fractal features of this set of zeros. And the reason that around roots of unity we see some black hole is because the root of unity is appears with high multiplicity. So in some sense they are kind of try to be equidistributed along this circle. And another very interesting feature that is not related maybe to Galois theory, if you look here on the, maybe you don't see what is here, on the real line there is a very thin line of real roots, because these polynomials have about some constant 2 over pi times log n real roots. So we can see some real roots here in this picture. So one motivation is just that it's really I don't know, beautiful that to understand the random polynomials and the roots, and Galois theory and discriminant in particular is the algebraic point of view of understanding the roots of these polynomials.
Wait, so are the roots the bright spots or the dark spots?
The brightness is how often they appear. I mean, if it's bright, it means that there are many roots with multiplicity. So you don't see it, but at 1 it's very bright. At the point 1, it's extremely bright because 1 is a 0 often.
Oh, so there's a 1 and then there's like a kind of a gap.
Yeah,
of roots.
yes. Yeah, because, yeah, exactly. Okay. So if I'll be more systematic, there are several conjectures that the discriminant plays a central role, and the probability that we are discussing play a central role. The first conjecture is the so-called van der Waerden conjecture, and this is in the what people call the large box model. In the large box model, we fix the degree of the polynomial, say something like 10 or 5. 5 is already very interesting, and we let the size of the box, the parameter that I called L, grow to infinity, and we're trying to understand what's going on there. And we know in this model that with probability that tends to 1, the Galois group will be the full symmetric group. This is, I don't know, goes maybe to Hilbert, certainly to van der Waerden. And van der Waerden asked in his paper, what is the second most probable group? So let's say that we throw away, we condition on the Galois group not to be SN. We look only on this set of probability that goes to 0, and we look what is the most frequent group there. And van der Waerden stated that he conjectures that the second most probable group will be Sn minus 1. This is a Galois group that tells you that the polynomial has a root, because we are looking on Galois groups as a group acting on the roots. And the probability that the Galois group is Sn minus 1 is something that is not extremely difficult to compute. So this is the van der Waerden conjecture, and in particular, if this conjecture is correct, then the probability will be a capital O of 1 over the size of the box, with some constant that depends on n. And sometimes people also refer to this weaker statement as the van der Waerden conjecture, although he stated the first one. And this conjecture was since the 30s, I think it was 36, there were several papers by van der Waarden in this in the 30s. So people started to work on trying to bound the probability that the Galois group is not SN as a first step toward this conjecture. Since then and until very recently where there were major breakthroughs. So I'm trying to be brief. So some names along the history that make significant progress is Knobloch, Gallagher, Zavine, Dittmann. Maybe you can see all the names. All of these made a significant progress, but in 2021, Manjul Bhargava proved the weak version of this conjecture, namely that it's O of 1 over the size of the box. So we proved that the probability that the Galois group is not SN equals the probability that it's either AN or SN minus 1. So the second most probable group is either AN or SN minus 1 with some explicit error term in L. And in particular, and maybe the more significant part or the major breakthrough was to prove that the probability that it's AN is bounded by a constant over L. So this was the major breakthrough, and this probability, if the Galois group is AN, the discriminant is in particular a square. Okay, so we see that this probability comes into play in the large box model. And we can ask ourselves how small, this is the question, how small is P and L in the large box model when L goes to infinity? And here we have a very naive heuristic that a few years ago I talked to several people and it was kind of convincing at the beginning, although it gave us the wrong answer. So you can think of the discriminant as a polynomial in the coefficients of degree. You can compute the degree using, for example, the Sylvester matrix. And so it's a polynomial of degree 2n minus 1. So, sorry, 2n minus 2 it should be. It's 2n minus 1, but the leading coefficient is 1, so it's not in the game. So the discriminant will be roughly L to the 2n minus 2. If I plug AI around L, then it will be roughly L to the 2n minus 2. I know that the discriminant is 1 or 0 mod 4, so it cannot be 2 or 3, but this is not something significant. So maybe this is the heuristic assumption, this is the naive heuristic assumption that the discriminant behave like a random number of the corresponding size, and the probability that a random number is a square is 1 over square root of it, right? So this will give us the answer that the probability should be, as L go to infinity, about L to the 1 minus n. But this is wrong heuristic. This number is way too small. And the main thing that fails here, or the thing that fails here, is that the discriminant doesn't behave like a random number because it has a lot of symmetries that raise the probability to have a square discriminant. Do you have questions about this heuristic? Okay, so it has many symmetries. Let me give you some symmetries. So for example, if n equals 0 mod 4, and the polynomials satisfy this kind of linear equation that f plus f prime equals some square of a polynomial, then you can just using very easy and elementary computation using properties of discriminant as presented as a resultant, show that this implies that the discriminant is a square. Now, when we found these symmetries at the beginning, we didn't believe that we are the first to find this amazing symmetry, this beautiful symmetry. But using these symmetries and similar symmetries with linear equations, we managed to give a lower bound, which is L to the minus n over 4. And in this lower bound, it's not really about, it's not only that the discriminant is a square, it's really that the Galois group is AN, which is slightly stronger. And then we looked in the literature and we went back, and at the end we found a paper of Hilbert that says that has similar symmetries, and said that Hurwitz told him about this symmetry. So it goes really back, this symmetry. And we exploited them to compute this. Another set of symmetries on square discriminant that we got give us a much stronger lower bound, which is L to the minus n over 2 minus a half. I ignore this epsilon. This bound only work for even ends. But the interesting thing about here we actually found a very specific family of polynomials. But the point is that all of the polynomials that we found here have a square discriminant, but none of them have a Galois group AN in the second example. And the point is that these polynomials come from a compositum of some polynomial of degree n over 2 with x squared. Okay, we can do some other kind of composition, but it always comes from composition. So this Galois group always preserve a partition of the roots into sets of pairs. And therefore the Galois group cannot be AN because AN doesn't preserve any non-trivial partition. So it's always a subgroup of some Ritz product, some imprimitive Ritz product. So an interesting conjecture that it's very naive, and I don't, I wanted to say something before that. If you see in this kind of examples and a phenomenon, and also in the previous one that I discussed, there is this power law. So we kind of expect that this kind of probabilities will behave like some power of the size of the box, maybe times some constant, maybe times some powers of log or something like this. But at least at the beginning, because we don't understand anything, we want to just understand what is the power that appears there. So this is this quantity. It kind of get rid of all these epsilons that I wrote before, because I don't want to write them anymore. And a naive conjecture that I think is very beautiful, but it seems to me extremely, I mean, I don't know any way to approach it, is that, so a naive conjecture says that the probability that the discriminant of a polynomial is a square should roughly be the same as the probability that the Galois group is AN, and this comes from the naive heuristic that Galois groups want, if they have a free will, they will decide to be as large as possible. But as you see in this example that in this lower bounds that I showed you, the stronger lower bound for P and L comes from non-AN groups. But it doesn't, it just mean that we don't know how to get other examples. But this is a naive conjecture that I don't have evidence for, but it feels right. So I wanted to share it with you. So what should we expect? What should be the power of the probability to have a square discriminant or to have a Galois group AN? So once I mean, the upper bound, the best that we have is 1 over L, and this is by Manjul Bhargava, and it's kind of summarize almost 100 years of progress. And the best lower bound that I know of is L to the minus n over 4 for Galois group AN. So if you don't know anything more, then probably you should do some numerics, and we did some numeric that gave us a very weak evidence for the following conjecture. I mean, I don't have a strong evidence, but a weak evidence that the power should be minus n over 2. And let me share with you a graph. So here the dots above are L to the minus n over 2. I mean, it's a log. It's a graph with all the sides are log. And the yellow, the dots below are the actual probability that the Galois group is A4. So it's degree 4 polynomials. And this is numeric done by two students, Noam Pirani and Ohad Avneri. And this is for L equal 1000. And we cannot go over all polynomials, so we just ran over 10 to 11 random polynomials. And the problem with the numeric is that almost always the polynomials have Galois group Sn. And if not, they have Galois group Sn minus 1. Okay, so to get something else, you need to search quite a lot. So here for 10 to 11 random polynomials, we found third. I mean, I'm talking about the last data point. This is the last data point. So we found only 30 instances of A4. And our algorithm kind of trying to sieve out the beginning, all kind of Sn by small, I mean, we use small primes we do a database of small primes in order to sieve out Sn polynomials quickly, but when the degree is 5, this becomes too much on the memory of our computer, and so even numeric is, at least for someone like me that is not an expert on numeric, is very difficult to do. But I think this graph is kind of convincing. I don't know. I'm not sure.
Quick question. I mean, n equals 4 seems very small.
Right.
Have you tried doing the same plot for n equals 3? Is there much of a change?
Yeah, but for n equals 3, by work of Dittman and
Yeah.
Chow, we kind of know the answer. And if I'm not sure if they know exactly, but it's something like minus 1.5. It's not exactly. I don't remember on the top of my head exactly. They did compute this kind of probabilities for small degrees, but I'm not sure I would expect that it's exactly minus n over 2 for n equals 3 or 4, but for n equal 10 maybe. And it's also very difficult because the logs that might appear there have a significant influence on the numeric. So it's very difficult to distinguish between log and L to the minus, I don't know.
Maybe
2 or 3
a challenge for some of the computational people in the audience. I know if there are a few of them, some data for n equals 5 would be nice.
Yes, and n equal 5 is, in my eyes, significantly more interesting than n equal 4, because there the Galois group is already non-solvable. For n equal 4 and 3, Dittman and Chow managed to exploit all kind of things in order to give better results. Although still we don't know everything there, even for small degrees.
Thank you.
More questions? Okay. So I see that Bjorn is in the audience. I hope that he's fine that I call it the Odelycko-Poonen conjecture. But I found it in this paper, at least for one model. So now we are in the restricted coefficient model. I wrote it before. So for example, think about L equal 1. So we choose the coefficient to be minus 1, 0, or 1 with probability 1/3. But I think in the original paper of Odelycko and Poonen, the coefficient were 0 or 1. And I wrote it incorrectly. Of course, we condition on the free coefficient. We demand that A0 is 1. Because otherwise there is a positive probability for A0 to be 0, and then the polynomial is not irreducible. So there is a typo here. It should be condition on A0 not being 0, okay? And then they conjecture that the probability should go to 1 as the degree go to infinity. okay? Except of this trivial thing that I forgot to write, that the free coefficient should be non-zero. Okay, and easy, for example, if we are in the case -1, 0, and 1, you can plug in for x3, and then you get a random number, so of size roughly 3 to the n. So the probability that this random number is prime is 1 over n. So essentially, you can push it back and get that the probability that f is irreducible is also 1 over n. Or even you can take a mod, you view this polynomial in mod 3, and then you don't even need analytic number theory because you use the prime polynomial theory. Okay, so it's easy to get a lower bound for this probability, 1 over n. We want to show that it goes to 0. We only show that it doesn't go to, we want to show the probability goes to 1. We only show that the probability doesn't go to 0 too fast. A much more elaborated work and a very seminal work in these studies is of Konyagin that showed that this probability is bigger than 1 over log n. And in several work of myself with Kozma and Koukoulopoulos, we managed to prove that the probability is actually 1 as long as the interval is of size 35 or more. So L is 17. When N is 17, the interval is 35. I'm really abbreviating all the history because I want to get to the question. And I think it's safe to put someone name on the conjecture because Brouillard and Variou showed that this conjecture is true under the GRH. So probably this is very strong evidence that the conjecture is correct. So all of the last 3 results are recent, and in fact you can go from irreducibility to Galois groups, and you can show, this is the work of Kozma and myself, that if you assume that the polynomial is irreducible, for example, you proved it, then the probability, then you can further deduce that the Galois group will be large, so it will be either AN or SN. And you see, this is exactly the problem that we had with the large box model. We go as far as we can. Sometimes it's easy, sometimes it's difficult, and then we get to the problem of understanding what happens with AN. AN is not easy to deal with, although the probability can be small, but we don't know how to prove it because the discriminant is complicated. So this is the motivation for the question, does this probability, so does P and L, the discriminant being a square in the restricted coefficient model, goes to 0 as the degree goes to infinity? For L equal 1 or 10 or 1 million, for any fixed L, it is open. Okay, so this was the motivation, and so based on the slide that I showed you before, a positive answer would imply a very nice result that even in the restricted coefficient model, the Galois group is SN. This we don't know even not under GRH. None of the method give us a way to get there. So these are the motivations, some of the motivations for these questions. And now I want to tell you a little bit what is known. I don't want to get into details, just to give you some feeling about things that going on inside the technicalities of these things. And I also, it's a surprise, I also want to tell you about the ongoing work, but I will get to it in the end. So one way to approach this problem, by the way, now it's a good time for questions if you haven't. Okay. So one way to approach it is to take the polynomial and reduce it modulo a prime. And hopefully modulo a prime, we have tools that can help us understanding something. And For example, if the discriminant is a square, then modulo a prime, the discriminant will still be a square. And when we work on finite fields, first of all, we take the uniform polynomials modulo finite fields. And there is a connection between the squareness of the property that the discriminant is a square and the Möbius function, which is the analog of the classical Möbius function in number theory. And I don't know exactly, I found some reference that it's due to Stickelberger and Swan, but I'm not sure that they are the first. I'm not sure about the correct credit on that. But this is a famous formula about the discriminant that you can express it in terms of the Möbius function. So let me clarify the symbols. FQ is a finite field. F with sub Q is a monic polynomial of degree n, and I assume that it's uniform for the rest of the slide. I mean, the formula that I gave you is a deterministic formula. And this symbol is, I'm not sure if it's a standard symbol, but it's a symbol that tells you whether A is a square, A is in the finite field FQ. It tells you whether it's a square or not a square, or zero if A is zero. Okay, like the Legendre, if Q was a prime, it was just a Legendre symbol. It would be just a Legendre symbol. And the Möbius is like the Möbius in number theory, namely, if the polynomial is a product of distinct primes, then it's just -1 to the number of prime factors. And if there exists a prime that its square divides f, then it's 0. So if it's non-square free, it's 0. And therefore, if you take Möbius square, you get the indicator function for square frees. Okay? So these are the symbols. And this is over function field. So this is for polynomial over a finite field. So I decorated all the symbols with a small q below to indicate that it's not the classical objects. And over polynomials over a finite field, it's a very nice thing, that I really like to teach, for example, in an elementary number theory course, that we have exact formula for the probability of the Möbius to be 0, 1, or -1. And it is exact formula. So for example, the probability that a polynomial is not square free is exactly 1 over q. I assume probably that n is bigger than 1, because for n equal 1, all polynomials are square free. And among the polynomials that are square free, the probability that the discriminant, the Möbius is a square or not a square, is exactly equal. And this is some kind of resembling exact formula in analytic number theory over the integers, but the exact formula are always in terms of zeros of zeta function. And this is because the analog of the zeta function for polynomials has no zeros. So we really get exact formula. Okay? All of this is elementary. And then the conclusion that we get from this is that the probability that a polynomial over a finite field have a non-zero square discriminant is roughly half, plus some error term that come from Möbius square, which here the implied constant, I think, is smaller than 1. It's not just an implied constant, it's really implied constant that's smaller than 1. So what happens if we use this conclusion, which is very elementary? We use this conclusion in understanding, say, the first question. So we know that for each prime modulo the prime, the probability, I mean, if I choose a polynomial in the large box model, it's really very easy to see that it's almost uniform modulo p for small p's, and then I get that the probability, if the discriminant was half, it would be half modulo all the primes. So I take enough primes and I get that the probability is as small as I want. So this is very easy to show using the corollary that I mentioned. If you want explicit bounds, then you probably want to use the large sieve inequality, which the big advantage here is that all the constants are explicit, and then we get some bound that is n to the cube divided by square root of L. This is the large sieve, or maybe larger sieve inequality. Okay. I might be lying a little bit with logs, but log L, but I hope you forgive me. So this is the result of Gallagher and Zavine. And what Bhargava did in order to prove his theorem was to control what happens modulo p squared by moving modulo p, and then he could improve the square root of L to L. I mean, he did a lot of things, just very, making it into a cartoon. Cartoonize it, I don't know. Okay. But the problem with the latter approach is that CN is not anymore explicit. I'm not sure he wrote exact bounds on the constant depending on n, but I think it's more than a polynomial if you go through the proof. So this result is much better in the large box model, but in the small box model, in the restricted coefficient model, it becomes less good because the dependence in n would be something like exponential probably. I don't know, but I didn't check it explicitly. Okay, so and this is a common phenomena that if you manage to improve on what the large sieve inequality give you, you get worse and worse bounds in n. And this kind of approach, this naive approach, doesn't seem to be too much applicable in the restricted coefficient model, except maybe, for example, if you take L equal 1, you can get that the probability that the Galois group is AN will be, that its SN will be bigger than a constant that come from just looking modulo 3, because there the polynomial is actually uniform. And this was used in the past. But you have only finitely many primes. Okay. So this, if you want to discuss the restricted coefficient, if you have in mind the restricted coefficient model, then you have to go and discuss non-uniform polynomials. So again, I take in L equal 1, for example, and then the coefficients are independent random variable with the values -1, 0, and 1. And what I need to study is how, if I want to understand the discriminant modulo primes, I need to understand how the random variable mu q fq is a random polynomial, but now it's not uniform because the coefficients are just -1, 0, and 1, and I look modulo large primes. Say p equal 11 or p equal 5 is already very difficult because it's a very sparse set of polynomials. Out of, if you look modulo 5, you have 5 to the n polynomials, but 5 to the n polynomials in total, but only 3 to the n, which is a very small it's a very sparse set of polynomials of our form. And then you want to understand how these random variables mu q fq distribute and mu q square fq distribute. So the first one deals with square-free polynomials, whether the discriminant is a square or not, and the second one checks whether you are square-free or not, whether the discriminant is 0 or not. Because if it's 0, it's very difficult to lift the information about the discriminant. Just mean that the prime is potentially ramified, not necessarily, but it doesn't tell us whether the discriminant is a square or not. Okay, so these are the questions we need to deal with, and if you are experienced in analytic number theory, you see that it's, I mean, first of all, you do translation from polynomials over finite field to integers, and then you want to, so the analog questions is how the Möbius and the Möbius square distribute on on a sparse set of integers, for example, integers that when you write them in a binary expansion, they missing some digit or something like this. And a very related work is the Maynard theorem on primes without the digit 7. And so these are kind of the tools that you need to translate and as transfer to function field and work. So this is work in progress, so I will not write it with Noam Goldgraber, who is here now. He's a student, a master student. Well, I'm not stating it explicitly because it's still in progress, but we showed that the discriminant of in the -101 coefficient, we showed that the discriminant is a square with probability close to half under some mild condition on the distribution of the coefficients. I mean, it's a Fourier type of condition, and then the application that we have in mind is the not so large model. So, I mean, this is the thing that I like the most in this talk, this name, and I think the credit is due to Noam. In one of the drafts, it sent it to me, and I like it so much, this name. So what is the not so large model? So the restricted coefficient model is when the size of the box is fixed and the degree go to infinity. The large box model is when the degree is fixed and the size go to infinity. And the not so large model, we let the degree goes to infinity, but also the size of the box maybe very, very slowly going to infinity. So it's all the middle cases. And what we are trying to achieve using what I showed before is to show that in this model, as long as we stay away from the restricted coefficient model, that there we don't know how to solve the problem. But in this model, the Galois group will be Sn with probability tending to 1, no matter how slowly L, the size of the box, go to infinity with the degree. And the idea of the proof is, first of all, if L goes fast to infinity, I wrote here n to the 4 because I forgot to correct it. It should be n to the 8. Square root of L should be n to the 4. But it doesn't matter. If L goes faster than polynomial to infinity, then we are actually in the large box model using if we use the result of Gallagher, for example. Okay? So when L grows fast to infinity, we are not worried because we are in the large box model. If L goes slowly to infinity, then we can use the method from the restricted coefficient model at least to say that the Galois group is either AN or SN with probability 1. So the only thing that we need to deal with is the discriminant. So the only thing that we need to show is that the discriminant goes to 0 as n goes to infinity. And the size of the box grows as slowly as you want. So this is exactly I think the one level above the restricted coefficient. And I will not get into the technical details, but actually I would get a little bit if you allow me. But the idea is that we use Fourier analysis, or if you want, exponential sums to compare the distribution of the random variables mu p f mod p and mu p square f mod p with the respective random variable for uniform polynomials, and then we can use the uniform case in order to prove our theorem. So if I have 50 minutes and you don't take the minutes that I was not here, I will tell you about a little bit about the Fourier analysis, or I can just skip to the end. What?
Yeah, no, that'd
Yeah,
be
let me
That'd be
decide.
wonderful.
What?
It'd be wonderful.
Okay, so I'll do it. Okay, so thank you, Rachel. So I will, again, I'm not going to get into details, just to give you some feeling. So how Fourier analysis is helpful here. So we have this random polynomial, and then you will also understand, I hope, why I say independent coefficient. It's written independent variables, but I mean independent coefficients, why they are so important. So the polynomial is a sum of independent random variables. So the distribution is the convolution of the respective measures. This is you learned it in the second day of Fourier analysis. Actually, I did it a long time ago. Maybe it was in the third lecture. So the distribution of sum of independent random variables is convolution of measures. And you know that Fourier transform maps a convolution to a product, right? So the Fourier coefficient will be product of Fourier coefficients. And the trivial character, I mean, the trivial coefficient will be responsible in some sense to the contribution of the uniform measure to our distribution. And we understand everything that happens with this trivial character. It will be just one because everything is probability measures. So the goal is to show that the other coefficients are small. And here we use this is the idea that probably appears in many places, but in this kind of context, I learned it from the paper of Maynard, who did it for the integers, but also in a paper of Bourgain about primes where you fix epsilon percentage of their digits. So it's also the same idea, similar idea appears, but it's a very, trivial idea that if you want to show, you have a product, you want to show that it's a small number, because its probability measure, all the coefficients are smaller or equal to 1. So you want to prove that the product is small, you just need a few of them to be less than 1, because the product of few numbers that are smaller than 1 will be very small, right? And this is the idea. You just need to show that a few of them is smaller than 1. And this was carried out. Yeah, I mean, it depends exactly what you want to prove. But for example, in the paper with Koukoulopoulos and Kozma, we managed to show this for any, I mean, enough, I say enough and closed. So let me give you a corollary for what we managed to do. So choose the distribution in any way that you want, just not being trivial. Then there will be a constant theta that depends on the way that you can choose, for example, that one coefficient will be 1 with probability 0.999 and the other will be 0 with the rest. So there will always be a constant theta such that FP will equidistribute in arithmetic progressions of modulus of degree at most theta n on average. So let me, maybe this slide was too technical, so let me finish with some concluding remarks. People study for a century now probabilistic Galois theory, and somehow from experience we learned that estimating the probability that the discriminant is a square plays a major role, and oftentimes is the major challenge in understanding what's going on. I try to a little bit show you that there are many tools and they come from diverse topics. I didn't made a comprehensive survey. I just touched a little bit of them, but there are many tools that were developed and are being developed now to study this kind of probabilities using all kind of areas. And therefore, in the recent years, the toolbox was expanded quite significantly by different people. So the tools are very, they are different. Let me say that. And the recent breakthrough that I surveyed some of them in the subject of probabilistic Galois theory give us a hope that maybe there is a hope for it give us hope for further progress by I mean I hope that many people are working. I know of many people that were working on this problem. And okay, I think I will finish here. Thank you very much for being a nice audience.
Thank you, Lior. Well, this is a good time for questions. Does anyone have a question? Well, maybe I could start with one. When you include 0 as one of the coefficients of the polynomial or exclude 0, is there any difference between what these probabilities and distributions look like?
Thank you, Rachel. So because we look on polynomials around zeros, then the low coefficient, for example, a0, a1, if a0 is 0, the polynomial, for example, is reducible. If a0 and a1 are 0, the discriminant will be 0, right? Because 0 will be a double root. But other than that, if you just demand that a0 is 1, then it already becomes insignificant. So other than this trivial obstructions or trivial consideration, I don't think there is a. It depends what you do, of course, but at least the method coming from Fourier analysis are not. They don't care what is exactly the distribution. So they work in general and they don't really see this. At least, yeah. So except the small coefficient, I don't think there is a big difference if 0 is included or excluded.
I don't know if this following question makes any sense or not, but has anyone ever looked at things where you instead fix the discriminant and then ask what the probability is that, among a certain set of polynomials, you have small coefficients? It's sort of like
Yeah.
do like a conditional thing or a backwards probability.
Right. So if you fix the discriminant, zero is very special, of course. So if you fix the discriminant to be 0, then this was studied in all cases, and we know. But if you fix it to be other integers, I think it becomes very difficult. Over a finite field, if you choose a polynomial uniformly and you make sure that the degree is coprime to the characteristic, or maybe the characteristic -1, then I think that the discriminant is actually also uniformly distributed. This is a result that Noam Goldgraber showed me recently do you remember by who, Noam? I have it open, I think. By Chan, Kwon, and Seaman, I hope I say their names, from 2018, that if the discriminant over a finite field, if there is some condition on the degree and the characteristic or the size of the finite field, then the discriminant is actually exactly, and the polynomial is uniform, the discriminant is actually uniformly distributed among the values. And this is the best I think.
Thank you. Any other
Thank you.
questions? All right, well, let's thank Lior again.
Thank you very much. It was a pleasure to be here. Thank you.